Okay, now we're going to do H10J.1, the second derivative. Okay, so last year or last time, you already know that the first derivative tells us if a graph is going up. So let's just say um, I'm just if I've got a graph that's going up, we know that the first derivative is positive, right? And if we've got a graph that's going down, we know the first derivative is a negative number, right? Um, all I care about is the sign. Is it positive? Is it negative? Now, um, so we can look at both of these, and we know for here it's going up, so we know the first derivative is positive. Okay, and here we know the first derivative is also positive because it's going up. Okay, the tangent line is going up for both of these. But the curves are different. Okay, so the change of the slope is getting steeper and steeper, right? It's the change of the slope is increasing. Here, the change of the slope is getting less and less steep. So the change of the slope is what we're going to be focusing on. And the change of the slope can be found with the second derivative. So here, it keeps increasing. We have a name for that. That's called concave up. Okay, this first example is concave up. When we see this decreasing like this, it keeps getting less and less steep. That's called concave down. And when I think of it, I think concave down is like a frown, whatever. Okay, so we've got this graph here. So consider this graph, y equals x minus 1 cubed. Okay, sketch the graph and label the intercepts. Okay, so I guess I didn't label the intercepts. Okay, this intercepts here at 1 comma 0. Okay, so take the derivative. So I'm going to call this thing inside here, I'm going to call this u. So I've got u is cubed. So the derivative of u cubed is 3u squared. And if u is x minus 1, the derivative of that is 1. Okay. So using the chain rule, we've got dy du times du dx. So that's going to be 3u squared times 1. And u is 1, x minus 1. Okay, so there's our first derivative. So we know when I've taken this derivative, is this ever going to be a negative value? I could plug in 0, something squared. Whatever you plug into x, we're always going to have a positive value. So if the first derivative is always positive, that means the slope is always positive. And you can even see in the picture, if I created a tangent, I created a tangent line here, a tangent line here, tangent line here, a tangent line here, it's always going up. It's never going down. That's why the first derivative is always positive. But you can see this here is different than this part here. Okay, and this, if I look at it this way, this looks like a frown, a sad face, boo-hoo. That's concave down. If I look over here, this looks like half of a smiley face. That's concave up. Now, but let's just not talk about it, how it looks, but let's do it mathematically with a derivative. So if I take the second derivative of this, okay, so we've got our y equals x minus 1 squared. So I'm going to say u is x minus 1, like we did over here, and I've got 3u squared. So I've got 3u squared. So the derivative of 3u squared, the 2 comes here, we get 6u. The derivative of x minus 1 is just going to be 1. If I use the chain rule, 6u times 1, and u is equal to x minus 1. So the derivative is 6 times x minus 1. So when x is equal to positive 1, then we're going to have, when x is 1 or greater, we're going to have a positive value for y. That's what fun. Okay. It's going to be positive value when for the second derivative. If x is less than 1, like if I plugged in 2, 0, -2, -3, if x is less than 1, then we're going to have a negative value for this. So when x is less than 1, well, here it's less than 1, this is going to give us concave down. And when x was greater than 1, this gave us concave up. Okay. Okay, so you might want to hit pause. Let's talk this through. What feature of the graph is indicated by the sign of the second derivative? So the sign of the second derivative indicates whether it's concave up or concave down. Okay, so the second derivative of this at x equals 1, the second derivative can be 0 when x equals 1. Okay. What is significant about this point in terms of concavity of the curve? So at x equals 1, the curve changes from concave down to concave up. That point is called an inflection point. Okay, so in fact I'm going to write that on here, this first page. This point right here is called inflection point. Okay, I'm going to give you a handout a little later on with the definitions and words that are very important to help us remember. Okay, so an inflection point is when the first derivative and second derivative both are equal to 0. Okay. Well, let's see. Okay. No. Okay. That's, that didn't make any sense. That was not correct. Okay, so given an equation of a curve that given the equation of a curve, how would you find a point of inflection if one exists? So a point of inflection happens when both the first derivative and the second derivative are equal to 0. The concavity on either side of the stationary point. Okay. So here we have concave up, and that's when the first derivative and the second derivative are both positive. Here we have concave up because the second derivative is positive. I might want to copy this down. So right now I'm looking at the shapes of the curves, and that's going to tell me if it's concave up or concave down. Okay. And here we have a stationary point. Stationary point is when the second derivative is 0 and um, and when but the first derivative just stays positive. Okay. I thought this picture was really good. I found this online. So concave up, think of this as holding water. You can hold water in this shape here. Concave down is when it's pointing down, it's dumping out all the water. Okay. So on my calculator for this one here, you type in your equation, and you can do second trace. You're very familiar with this, I know. You do minimum, and if we want to find the minimum of my graph of this equation, enter left bound, right bound, guess. Okay, and there's my minimums. So these dots right here are our minimums, and second trace forward from maximum, that's going to give us maximums right there. And we have an inflection point right here. Okay. So how do we figure out the inflection point? To figure out the inflection point, because right here we have concave down, right? And then these parts, we've got concave up. So this inflection point is when it stops being concave down and starts being concave up. So to figure out these inflection points, we have to make the second derivative equal to 0. So my function is x to the fourth minus 3x squared plus 2. So my first derivative, I get this. My second derivative, I get this. And we want to make the second derivative equal to 0 to find our inflection point. So now I can say, okay, so let's make 2x squared minus 1 equal to 0. I can add 1 on both sides, divide by 2, and I have x squared equals 1/2. So I take the square root of both sides, I take the square root, and I end up with plus and minus square root of 1/2. So I know that at this point right here, x is negative 0.707, and at this point right here, x is positive 0.707. Okay, so that's where it's concave down, is in between those 2 points. And you can see it in the shape of the graph as well. Okay. So you may want to read this. I think this is useful and important. But from our reflection, a point is a local maximum when the second derivative is negative. So a point is a local maximum when the second derivative is negative. And a point is a local minimum when the second derivative is positive. Okay. So let's talk this through. Find the first derivative. Okay, that should be a piece of cake. Okay, hence find the coordinates of the point on the curve when the first derivative is 0. So if I want to find when the first derivative is 0, I I can factor out 6 here first, right? And then I can see, oh, this is factorable. This is x minus 2 times x minus 1. So I know when x is 2 and when x is 1, we're going to have something happen on this graph. So 1 and 2. Okay, from this picture, we can see at 1, we're going to have a maximum, and at 2, we're going to have a minimum. But let's just do some math first. So if I want to find the coordinates, I also need to find the y value when x is 2 and when x is 1. So when x is 1, if I plug in 1 into my original function, so here's the original function. If I plug in 1 into the original function, I end up with 10. So the coordinates at this maximum is 1, comma 10. Okay. And I don't know what color to use, but I'll use orange. Okay. And if I plug in 2 into my original function, I'm going to end up with 9. Okay, so that coordinate is 2, comma 9. Okay. Now, let's find the second derivative. So this, if I've got my equation y prime equals 6x squared minus 18x plus 12, if I take the second derivative of that, I end up with 12x minus 18. So we want to find out whether the points are local maximums or minimums. So I can take the second derivative and factor this out, and then I see that the second derivative is going to be 0 when x equals 1.5, or 3 halves. So if x is smaller than 3 halves, then I'm going to have a negative value for the second derivative. If x is bigger than 1.5, I'm going to have a positive value for the second derivative. Okay, so that means at 3.5 we have an inflection point. So for our negative values here of our second derivative, that causes this to be concave down. And so like this portion right here is concave down. You can even see it looks like a sad face. Boo hoo hoo. And so if our value is greater than 1.5, it's going to be concave up. It's sunny, it's happy. And you can see this looks like a happy face until it gets to the inflection point. Okay. Find the coordinates of the point of inflection. So we're going to put 1.5 back into the original equation, because we know the inflection point happens at 1.5, because that is when the second derivative is 0. So I plug in 1.5 back into the original equation, and I get 9.5. So this inflection point happens at 1.5, comma 9.5. So the domain of when it's concave up is for the values greater than 1.5, and the domain of the values concave down is when x is less than 1.5. So this inflection point we said right here is 1.5, comma 9.5. Okay. Might hit pause if you need to. Okay, next page. Man, I'm tired. Okay. I'm just going to talk this through. Find the local maximums and minimums on the curve. So we just do this graph here. My first derivative gives me this. And so I know that the zeros, the first derivative is 0 when x is 0. And we also know that the first derivative is 0 at 1.06. You can tell from the graph here, when x is 0, we're going to have a maximum, a local maximum. When x is at 1.06, we're going to have a local minimum. Okay, we can get these points here by plugging in the 0 into the original function, and here I can plug in 1.6 into the original function. You can also find these values when you do second trace, and if you do second trace, this will tell us the minimum and maximum values here. Okay. Question B, find the point of inflection. The point of inflection happens when the second derivative is 0. I take the second derivative, I make it equal to 0. Okay. And then to find the coordinate of the inflection point, I plug the x value that we just found, I plug it back into the original equation, and now I've got the coordinate for the inflection point. Okay, now it says hence find out when it's concave up. So it's concave up when x is greater than 0.669. And you can tell it even looks that way. So 0.669, sort of like right in here somewhere. You can tell that kind of somewhere in between those two dots, it goes from being concave down now to concave up. Okay. They ask us to find the first derivative. Part 2 says find the second derivative. It looks a little messy. And then hence show that the minimum point is at x equals 1. So what I did here is if you plug, we want to find when the second derivative is equal to 0. We're going to know we've got a maximum or a minimum. So to make the second derivative equal to 0, okay, I don't know what I'm saying. Okay, when x is equal to positive 1, we know that the slope is 0 for the first derivative. So if the slope is 0, we know it's going to be a minimum or a maximum. So that was wrong. It should have been a single mark because it's the first derivative. Okay, so we make a sign diagram, and we know that this is for values less than 1, we're going to get a negative value. And for our slope is going down, right? For values greater than 1, I picked like 2, and we end up with a positive slope. So if it goes from a negative slope to a positive slope, that means it's going to be a minimum. It's going down. Okay, and when I take the second derivative, we get this messy looking thing. And since this can't ever be equal to 0, I can't have x be equal to 0, and this doesn't factor out. So since this can't ever equal 0, that means there are no inflection points. And I'm going to call it quits there.